Oh. Only two things.
Yeah.
Oh, that was me. I thought that 2 would be sufficient. They were all circled.
that seems right. Sorry, I've been slacking a little bit on showing up early to help rearrange the desk. Thank you for taking the initiative there. You can really tell that chalkboards are not in vogue. People barely know how to use them these days.
I do wonder how they clean them to be like, what's in the top left corner and at the bottom left. Like, get them that clean. Do they? The janitors do it, right?
Yeah, it's usually just a wet cloth.
Okay.
The only thing to watch out for in case you have to use a chalkboard later in your career is don't write on it while it's still wet, because then it becomes much harder to erase.
I feel like I would hate the feeling of chalk dust on my hands. Like,
You get used to it.
Have you ever tried those like Japanese, like expensive?
Cool?
Yeah. That stuff is great.
is that one of them?
Yeah, I bring one.
Is that like the original, or is that like the replacement knockoff?
I have a few originals left. These are the knockoffs, which are still better than the standard Crayola that the university provides. But yeah. Okay. Anyway, we should begin. A couple of things, just logistically. If you look at the guidelines that I sent out, the proposed date for the presentations that you all will make was the Friday after classes end, which what I was trying to do there is just be, maybe kinder so that you could leave sooner. Although I've been told that maybe this isn't ideal. Our original final exam slot was scheduled for the following Tuesday, December 14th. I've asked a few of you individually if it would be acceptable if we just used that time and extended it slightly to have our final presentations. Of course, this goes along with the original proposition that I made that I would provide us some meal during the time that we made our final presentations. Is that okay? Does that agree with everybody? I think it would be from like 1 to sometime before 5 p.m. And I'm allowing for time for questions, and I know that's a long time, but hopefully a meal would be okay. Yeah.
And what about like the homework solutions and stuff like that? Because you said there was like extra credit available.
Yeah, that's
I want to
right.
make sure that doesn't like whether we have it before grades close.
Yeah. So grades aren't due until the following week.
Okay.
So whatever problems you write, just give them to me by that time, and then everybody will have a few more days to work on whatever problems are proposed, and then I'll grade those accordingly. And I know that the timeline's kind of tight. Maybe it's less than ideal, but hopefully that's okay with everyone. Good. Okay. So then we'll do that. Scrap the timeline that I gave in the guidelines, and we'll push our presentations to an extended version of our scheduled final block. Also, I'll send out a survey later this evening for what we would like to have to eat during that time. I was thinking maybe like Indian food or Thai food. maybe. But yeah, I'll ask you all to discreetly give me your dietary restrictions and we can decide from there. I'm open to suggestions too, if you have a particular thing that you like. I'll, of course, take that under consideration. Right, so, as usual, I've been struggling to devise an interesting problem set. My best efforts should come to bear this evening, I hope. And then you'll have the usual week. It'll be due the following Wednesday, right before Thanksgiving break. And then we'll have one more problem set after that. Okay, I think that takes care of all the logistical things. Right, and of course, many of you have already talked to me about what you would like to do for your final project, but if you haven't yet, just send me a quick email sometime before the end of the day, say. It's not really of vital importance, but I just want to make sure that nobody overlaps too much. And I know I haven't replied to everybody in full measure, but again, do my best to do that by tonight. Okay, any questions related to any of those logistics? Okay, great. So, where were we in our discussion? By my estimation, I think the last thing we did was justify a claim that we made in the first couple weeks of class that an analytic function has components which possess continuous partial derivatives of all order. Right? Okay. Oh, actually, no, we said the generalized Cauchy formula after that. Right, sorry. Yeah, I'm a bit frazzled just because of panicked Calculus 3 students. Okay, so let's put the generalized Cauchy formula to some examples. Let's see how this helps us compute certain integrals rather quickly. So, let's compute the integral along gamma of e to the 5z divided by z cubed dz. Of course, I have to tell you what gamma is. Where gamma is the piecewise smooth, closed, oriented curve that traces out the unit circle traversed once. Once counterclockwise. That is positively oriented. Which of course is a necessary condition for us to be able to apply the Cauchy integral formula. Right? Otherwise we just add a negative sign. Or, sorry, multiply in a negative sign, as per usual. Okay, so this is, we could try to approach this in our usual way using the brute force method by substituting in a parameterization of this curve, but that rapidly becomes quite messy, right? Because we have e to the 5z, and if we parameterize the circle in the standard way, we use e to the it, right? For a circle of radius 1, centered at 0, I should say, yeah.
Just a question. I would never do this because it would be kind of pointless, but can you apply the normal rules of integration, like integration like the parts there before you substitute representations?
That's actually a really good question. Does there exist an analogous theorem of integration by parts for line integrals? I don't know the answer to that off the top of my head. My intuition says that the answer is yes, regarding a choice of parameterization, right? It won't depend on that choice, but to actually write an effective formula, you have to make some hypothetical choice, is my guess. I don't know the answer to that. That's something worth looking into. Okay, good. However, let's just compute this quickly by using the generalized Cauchy integral formula. Okay, so that is to say, when we write this in the standard form, right, I'll just say that the integral along gamma of e to the 5z divided by z cubed dz is equal to, remember, I think the very last thing I said was we state the Cauchy integral formula as some integral times 1 over 2 pi I, blah, 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 but we rewrite it usually if we want to compute an actual integral. So this is equal to 2 pi I divided by m minus 1, what's m here? 3, right? The power of the, maybe I should say this in a more advanced way, the order of the pole of my integrand, minus 1, factorial, 2 factorial, times the second derivative of f evaluated at 0. What's f?
E to the 5z.
Yeah, the analytic function that I'm considering on the interior of gamma. Okay, so that is to say, what's the second derivative of e to the 5z?
25 e to the 5z.
Yeah, exactly. Okay, and what is that second derivative evaluated at 0?
25.
It's just 25, yeah. So altogether, what we get is 25i. Of course, our 2's cancel here.
Is there any reason why we picked 0?
Yeah, that's where the pole is. This integrand has a pole at 0.
So that if we were to write in like the formula, it'd be like z minus 0 to the third, which is
Precisely.
z not 0.
Yeah.
Oh, okay.
No, that's fine. That's
So-
it's a valid question. I skipped an algebraic step, but yeah, that's exactly right. We're considering z minus 0 to the third.
Yeah, I just think I wrote the formula down wrong.
Sorry, say that again.
I think I wrote the formula down from last class wrong. Is it 2 pi I the mth minus 1 derivative of f evaluated at z naught?
Yeah.
Okay.
Well, okay, so yeah, we made this change, this formal change of coordinates, zeta, z went to zeta, and z naught went to z, right? So, and then the very last thing we did was switch back to that. So yes, we're evaluating our m minus first derivative at z naught. When we change back to our original coordinate system, after we did this formal trickery to deduce the generalized Cauchy integral formula. Okay, good. Here's another example. Let's calculate the integral along C of 2 times z minus plus 1, what am I saying? Divided by z times z minus 1 squared dz. Let me tell you what c is, where c is pictured as the following curve. Um, Okay. So, how do we begin to analyze this problem? How can we start to try to calculate this integral, this contour integral?
Where exactly does one fall in that?
Good question. I didn't draw this to scale in the least. Here's one.
And yeah, so partial fractions.
So, we can actually use the integral formula to avoid having to do partial fractions in this case. This is because of what we can recognize this curve as. First of all, notice that this curve C is not simple. That is to say, it's not too hard to recognize the fact that you can't continuously deform this into a simple curve. However, we can think of this curve C as a union of simple curves. Right? That is to say, we'll consider, here's the trick, we'll take, so this whole thing is C, but let me take this to be gamma 1, which has positive orientation. And I'll take this second part to be gamma 2, which has negative orientation. Right? So I can traverse one and then the other. Say, for example, by taking this point of self-intersection as my starting point. Oh, sorry, wrong way. I'll traverse gamma 1 and then traverse gamma 2. That's the same as C, right? This is where we're invoking the fact that our contour integrals are independent of the parameterization of the curve, right? So I can decide to break this up into a pair of simple closed curves.
Is this a similar idea to how originally, when we were talking about gammas, we would break it up into the small and the lowercase gammas?
Yeah,
And say it's like the sum of those, and the same way as C is it's sum kind of these two gammas.
exactly the same. We choose to, because we took the painstaking effort to show that our contour integrals were independent of the way in which we parameterize our curves, we can do such breaking up. Okay. Good. Okay, so that is to say, let's record your comment. This C is equal to gamma 1 plus gamma 2. Okay, so just in terms of the definitions we made for our contour integrals, the integral along C of 2z plus 1 divided by z times z minus 1 squared dz is equal to the integral along gamma 1 of, I'll write this very suggestively, 2z plus 1 divided by z divided by z minus 1 squared dz plus the integral along gamma 2 of 2z plus 1 divided by z minus 1 squared divided by z dz. Explain to me why I chose to break it up this way.
Because now for gamma 1, we avoid the pole. For gamma 2, we also avoid the pole. And now they're
Exactly.
simply connected.
Exactly. Right. Our original integrand has poles at 0 and 1. So now I'm in, again, this goes back to the standard example, that start example from a week and a half ago, right, where I know how to calculate the integral around a contour that contains a pole. Right. Okay, good. So, this is kind of the magic, right? We can do this mechanically, even though we don't really have a good way of picturing what a complex function graph is. Which is like, when we study calculus of a real variable, that's kind of how we build our intuition of what integration is, right? We look at a graph and we find the area underneath this graph, right? So this machinery that we've been building now allows us to calculate, give meaning to an integral of a complex function without having any notion of it. It's quite just computational. Right? Okay, so let's actually calculate this thing, find the value of this integral. So the integral along gamma 1, so I have a pole of order 2 here, right? So I'll apply the generalized Cauchy integral formula to say the following for the integral along gamma 1. 2 pi I divided by 1 factorial. I'm just going to be very explicit here, just to illustrate the point. Times the integral with respect to z of the integrand. I'm sorry, not the integrand, the numerator function. The thing that's analytic in the interior of gamma 1. Okay. Yeah. Now, I'll take this derivative evaluated at the pole that the contour contains, that gamma 1 contains. Now, the only thing to be careful of here is remember that gamma 2 is negatively oriented. So in order to apply the generalized Cauchy integral formula, we have to throw in a negative sign. Okay, so minus, oh, sorry, this is not spaced very well. Just gonna slant on down. Minus 2 pi I divided by, what's my order of this pole? It's 1, so that gives me a 0 factorial, which by definition is just 1. Right? Times the derivative with respect to z of 2z plus 1 divided by z minus 1 squared, evaluated at the pole that gamma 2 contains, z equals 0. Yes?
Do we consider the derivative or do we just consider the function? Because it's the 0th derivative, right?
Oh, I'm sorry, you're right.
Yeah.
Yeah, exactly. Again, the order of the pole is 1, so we take the 0th derivative or just the function itself. Thank you. Okay, good. So, you take the time to do this algebra. What do you get? negative 4 pi I. You know, use the quotient rule here and just evaluate this function at z equals 0. And you get this. Okay, good. Okay, so now we're going to enter into a more serious discussion about how to bound analytic functions. And we've talked a little bit about bounding integrals. But as a matter of fact, we can deduce a lot more about how analytic functions behave. Remember, the broad theme of what we've been doing over the past several classes is that the condition of analyticity makes derivatives and integrals intimately related in some way. Okay? So, in fact, we can come up with some effective bounds on how analytic functions behave in their domain of analyticity. And this machinery that we develop will finally allow us to prove the fundamental theorem of algebra, that over the complex numbers, every polynomial of degree n has exactly n solutions. Finally, we can say a proof of this, right? Which I'll remind you, it is the main thrust of Gauss's doctoral thesis, right? Also, interestingly enough, he is widely regarded as the first mathematician that considered complex numbers as a valid construction and used them to their full capability, so many would say. So this is kind of exciting. We can see some reflection of this. Okay, so let's discuss bounds on analytic functions. Let's get right into it. Here's a theorem. So let's assume that f, the analytic on and inside circle C sub r of radius r. Centered at Z naught. Then here's something that we can say. If the modulus of f of z is bounded by some real constant m for all z lying on the circle C sub r, then we must have the modulus of the nth derivative of f evaluated at z naught is less than or equal to n factorial times m divided by r to the n. Or n positive. Well, sorry. I should, well, this is okay. I was gonna say, maybe I should say non-negative here, but of course, that was the assumption. N is 0. Yeah.
Is C sub R closed?
Yeah, it's a circle. So, uh, actually, I'm glad you asked that question because one of the problems that I'm going to include on the next problem set makes quite the fuss over what are the starting and ending points of a parameterization of a circle. But yes, we're assuming that C is closed here.
So for Z as a member of CR, it means Z also includes, or the boundaries also include the possible Z's.
The possibility of what?
For Z, so Z in R, or CR, that means it includes the boundary.
Oh yeah, this means that Z is
Yeah.
on the boundary of this is it's on
Okay.
the circle
Yeah.
itself.
Okay, so just,
Yeah, I'm not saying that this lies in the interior
Yeah,
of
yeah.
C. It's actually on the curve itself.
If it was gonna be in the interior, C would be a disk, not circle, or is that?
Yeah, exactly. If I were to specify a disk, then this would be ambiguous. Like what I meant, whether it was on the boundary or the interior. But because we're actually considering the curve itself, I'm saying that we're looking at a point on the boundary. Okay, good. Okay. Right. So we'll prove this. It's not all that difficult given the generalized Cauchy integral formula, but this has vast implications, which we'll spend much time discussing. So let us positively orient CR. I haven't specified an orientation. Let's choose a positive orientation, which is unambiguous. Then the general Cauchy integral formula says what? Write this on the next board. The nth derivative of f evaluated at z naught is equal to n factorial divided by 2 pi I times the integral along the circle of radius r of zeta divided by zeta minus z naught to the n plus 1. Right, we go down an integer. We use the formula e zeta. For for zeta on the circle. Again, same notational convention we were just discussing.
Is there a reason we use zeta instead of z? Just like,
No.
okay, like back in the theorem we say z, here we say zeta.
So again, so zeta naught is a specific value. I know we did this formal coordinate change. Again, no is really the answer.
Okay.
I'm sorry for any inconsistencies that arise from this, but I don't think there will be any, as a matter of fact. Okay? So, right, this is true for zeta on gamma. The integrand is bounded. In modulus by the following. M divided by r to the n plus 1. And the length of CR is what? 2 by r, yeah. Now we'll appeal to our only essential bounding theorem for integrals, right?
Can you quickly comment why the integrand is bounded on this?
Yeah, so here we have M appearing because,
so we're just taking that.
say again,
So it's like we're just using that condition there.
we're using this condition, and the fact that zeta lies on CR tells us that this must be R, right? Because we're centered at Z naught.
Okay, yes.
So we can't be further away or closer than R away from Z naught. And I probably should have wrote down to say that, but yeah, that's the reason why. Is that okay with everyone? Good. Okay, so now we can just appeal to our standard bounds on the modulus of an integral, right? Okay. So this implies that the modulus of nth derivative of f evaluated at z naught is less than or equal to the bound of the modulus of my integrand times the length of the contour C sub r, or written more compactly. Oh wait, I'm sorry, I forgot a term here, right? Still have my constant term out front, n factorial divided by 2 pi I. Let me correct that. N factorial divided by 2 pi I times m over r to the n plus 1 times 2 pi r, or written more compactly, what do we get? N factorial times m divided by power raised to the n power.
What happens to the I?
Oh, good question. What?
I think you might need to take the modulus.
That's right, of course, I take the modulus here. So what's the modulus of n factorial divided by 2 pi I? It's just n factorial divided by 2 pi. Sorry. Yeah, good. Okay. Great. Now, here's the first major surprising consequence of this bounding theorem. Which is due to a mathematician named Liouville, who, as my understanding goes, was the first person to compute the area under a Gaussian distribution, which is somewhat surprising because it's a region of the plane which is not finite, but yet has a finite area. This is kind of interesting. If you, when I teach calculus 3, I always make an important point to show how you can compute this using a double integral. You might have seen this in calculus, right?
You have to know the area is 1 in order to use the distribution.
Yes.
So then, like, why did the distribution exist before?
Because not everybody is a mathematician. Right? It works. But proving that fact took some additional mathematical work. Yeah, good question. I don't know. If only it were the case that everybody rigorously proved everything that they used. It's not the world we live in. So here's this surprising fact. Which, again, is usually attributed to Liouville. The only bounded analytic functions sorry, let me strike that. The only bounded entire functions, by which I mean analytic on the whole plane. Functions. Are the constant functions. Okay, so, I gave you this very broad and general definition of what an analytic function is at the outset of late September or early October. And now we're successively paring down the properties that such a function must possess. Turns out it's quite constrained what an analytic function can be. In case you weren't convinced of that already, here's even more evidence. Okay, so let's prove this. Let's assume, of course, that, as we said, that f is analytic on C. And the modulus of f of z is bounded by m. Okay, I should take an aside here. Of course, when I say a bounded entire function, of course I mean that the modulus is bounded, right? And the textbook kind of like slides this casually past you. Of course, we don't have a way of comparing arbitrary complex numbers, so we have to take the modulus to have a relevant notion of bounding, right? So yeah, I even wrote this down, and I forgot to say it until now. But what do I mean by bounded? I mean bounded in modulus. Okay, right, so, by our last theorem, what this tells us is that the modulus of f prime evaluated at z naught is less than or equal to m divided by r. Holds for all r. Right? What am I really saying here? If I take an arbitrary point z naught and look at a circle of radius r centered at z naught, then I know this bound must hold by my last theorem. What do I do now? Yeah, what happens as the limit as r goes to infinity? Well, what does that get us? It implies that the modulus of f prime at d naught is less than or equal to 0, which in turn implies that f vanishes everywhere. Yeah, sorry, thanks. Which in turn implies f is constant. Okay. So, I think this is a good time for a break. And then when we come back, we'll prove the fundamental theorem of algebra, that every polynomial, we'll prove actually a slightly weaker thing, that every polynomial with complex coefficients has a root in C, which simple inductive argument will allow you to prove that it must have exactly n roots. Okay. is the end of everyone's term going?
Not terrible.
Not terrible.
Not terrible.
Good. Good.
One of my professors just told me that he's planning an exam for December 1st because it's the last day he's allowed to.
Mm-hmm.
Which is,
It's terrible.
yeah, I don't know why he felt the need to tell me that. But
Yeah, there was at least in the math department, there was a mass emailing to all the instructors that this is the last day you're allowed to give an exam, because apparently that's been quite the issue in the past, that students complain, it's like, oh, not supposed to have an exam until this time.
Everyone give the exam on the first. That'll be making it so much better.
Yeah, right. For everybody, right? Not only the students, but now those of us teaching multiple classes will have to grade multiple exams for different classes.
Yeah.
It's quantum would definitely help.
And in quantum, you use Fourier series to convert between position spaces and momentum spaces.
Yeah, that's pretty much all you use it for.
Did you give back all the exams on Friday?
Yes, I have your exam
Awesome.
as well.
What do you think
Thank
the
you.
best mathematician of all time? Is it Gauss?
Awesome, thanks.
That's a tough one.
That's
That's a question.
like asking me I should give a message.
Euler.
Well, really, think about what you're asking here. I have no purview to answer that question because I'm stuck in a certain time. I can't know what will happen in the future. If you're really considering all time, I don't know, there's no way for me to give anything close to an answer to that.
Then who's your favorite mathematician? Do you have a favorite?
Dedekind. Richard Dedekind.
What's he know?
You said Dedekind cut, right? Yeah. This is some certain definition of the real numbers, which is parallel yet slightly different than the definition that depends on convergence of Cauchy sequences. Okay, like in the classical literature, these result in equivalent ideas of the real numbers. However, when you work in an intuitionistic framework, i.e. a system of logic that does not permit the law of the excluded middle, i.e. That is to say, every statement is either true or false. I'm generalizing a lot of things here, but when you work in an intuitionistic framework, the notion of the Cauchy completion that results in the reals from the rationals and the notion of Dedekind cut produce two distinct algebraic objects, which is really interesting to me.
Do they both satisfy the axioms of the real?
What are the axioms of the real numbers? What is allowed or not allowed, depending on whether you admit the law of the excluded middle.
Does that total order?
Sometimes. Okay. Feel free to contact me about logic anytime. That's really the spirit of my research. So, happy to elaborate on that. Not during class. Okay, so let's get to the fundamental theorem of algebra. Well, first of all, let's think about polynomials in regard to what we just proved, Liouville's theorem. Polynomials are non-constant analytic functions. what does this tell us? That the modulus of a polynomial must be unbounded, right? So, that is to say they have unbounded modulus. Yeah, right. Of course, we did say entire functions. I should say that, right? Let's see. Yeah, good. So let's let P of Z. Let's give some names to what P of Z actually is. Okay. Where I'll assume that my leading coefficient is not equal to 0. That is to say, necessarily I'm taking the degree of P of Z to be n. Okay. Then we can rewrite P of Z as follows. Factored out a factor of z to the n, which why do I bother doing this? Well, we're going to build greatly on top of this. Remember I mentioned this notion of Laurent series, where we will try to come up with a series representation of a function that is similar to a power series, but will allow negative powers. So this is some preview of the type of manipulation that we'll do. Okay. And furthermore, as the modulus of z tends to infinity, then P of z divided by z to the n actually equals a sub n. Right? Okay. So, just to remind ourselves, let's say what the fundamental theorem of algebra is. Okay, every non-constant polynomial with complex coefficients has at least one zero. Okay, so before we actually commit the proof of this, just take a second to reflect as to why this shows that every complex polynomial of degree n, which is non-constant, that is to say we're excluding the case where n is equal to 0, must have n zeros. Why is that?
factor the zero out, and then your new polynomial still has to have
Exactly.
one zero.
Exactly. We can use the division algorithm. As is typical of profound results in mathematics, they rely on very mundane things. And once we show the existence of some root, we can successively apply the division algorithm and get polynomials of lower and lower degree. Okay. Okay, so as we were saying, we'll have p in the standard form, a times z to the n up through summed up through a0. Let's assume that some polynomial which has degree n, where n is not equal to 0, is not equal to 0 for all complex z. Okay? Well, one thing that this tells us is that the function f of z, which is 1 over the polynomial p of z, is entire. Right? The only way we could introduce any poles to this new function f is if the polynomial p was 0 somewhere for some z. No. Okay? So, furthermore, we know that the magnitude of p of z divided by z to the n, the modulus, as we've been saying all term, is greater than or equal to, for example, the modulus of a sub n divided by 2, right? I know that thanks to the derivation that the seemingly trivial derivation that I just made here, right? Okay? I should say, for z large enough, right? So of course, this statement I was making is a limit statement. It's an asymptotic statement. So that is to say, if I pick z big enough, I can guarantee that the modulus of this expression must be greater than some size. And I picked this size for a reason, which we'll shortly see. Okay? For large enough z, let's say, just to give this a name, the modulus of z is greater than or equal to rho. Just attaching a name to this so we can compute with it. Okay. All right, so what this implies is that the modulus of f of z is less than or equal to 1 over the modulus of p of z, which is, by our bound that we just constructed, less than or equal to 2 divided by the modulus of z to the n times the modulus of a sub n, which is less than or equal to 2 divided by rho to the n times the modulus of a sub n. Okay, so in other words, what we've shown is that outside of a disk of radius rho, our function f is bounded. Right? So now you can tell me what our next step is in this proof. It might not be totally transparent where I'm going here, but let me know if you can see it.
We're trying to show like whenever E of Z is constant.
Yeah, right. And how will we do that? We're in a certain sense halfway there. We've shown that for some region of C, our function f is bounded.
To show that it applies to all of us.
Yeah, so we have to take the rest of C and show that our function f is bounded there as well. And if it's bounded everywhere, then it has to be constant.
Do we take rho goes to
So we've essentially already covered that case, right? Because we're saying that this applies for z greater than rho. Now we have to look inside the disk of radius rho. Okay, and then as it turns out, it doesn't matter that we have different bounds inside and outside that disk. Just take the maximum of whichever one it is, and you're still bounded everywhere. Right? Okay. The modulus of z less than or equal to rho. This is a standard old result from Calculus 1. What can you tell me about the function, the modulus of f of z? This is a bit of a trick question, because the thing I'm asking you to produce is, in a certain sense, so obvious that you might not think of it.
What's the f of rho?
Even more basic than that, just a property of this function.
less than f of rho?
So,
Well, less than some constant.
Actually, no. It's less than f of modulus of z.
this is a continuous real valued function, right? It's real valued. The modulus, when I take the modulus of a complex number, I get a real number. And f is analytic. So f itself is continuous. Ooh, maybe I'm glossing over a slight detail. Taking the modulus is a continuous function as well. Okay, so this is a continuous real valued function. Okay, that's a step. Now, what do I know about this region? It's modulus of z less than or equal to rho.
It's bounded. It includes zero points.
It's bounded and closed.
Yeah.
Exactly. It's compact.
So the max is on that set.
The extreme value theorem. A continuous real valued function attains its maximum on a compact set, on a closed and bounded set. You might not have heard that formulation of it before, but this is integral to doing optimization problems throughout calculus. Okay? So, and modulus z less than rho, less than or equal to rho, specifies a compact set. So, the extreme value theorem implies that the modulus of f of z achieves a maximum. Okay, so our two, we've broken the complex plane up into two pieces. Those parts, those points, those complex numbers which have modulus greater than rho, greater than or equal to rho, and those complex numbers which have modulus less than or equal to rho. We've come up with bounds for both of those regions. Okay, so this implies that f of z is bounded and entire. So constant thus p of z is constant. So we're done. Yeah. Good. Yeah. So there's kind of I would say there's a love-hate relationship going on here. You know, we aren't able to write down a single bound for this function f. But if we can do it piecewise, component-wise, that suffices. Right? This is fairly abstract in a certain sense, which is clever and nice, but it's not the first thing you would think of. Okay. So, good. So now we can say something more about where if a function f is analytic in some domain D, we're very close to being able to say where f attains its maximum value on D. Right? This is some kind of analog to the extreme value theorem. And we can say more because analyticity is a much stronger condition than continuity. So, and you might be able to guess right away what additional conditions we must insist on some analytic function in a domain D to attain a maximum value. We have to assume that our domain is bounded in analogy with what we just were talking about with the extreme value theorem, right? Okay. Here's a lemma. Suppose f is analytic in a disk. Start very specific. centered at Z naught. And the maximum value of the modulus of f of z over the disk is, oh no, let's just say it happens to occur at the center of the disk. Z naught. Then, the modulus of f of z is constant in the disk. Okay, so I'm going to ask you to prove this on the next homework. But I'll give you some guidance first. Okay, I'm going to give you an intuitive argument, and then you'll produce for me a formal argument. Here's a proofish thing. Assume, by contradiction, that the modulus of f of z is non-constant. Okay. Then there must exist a complex number Z1 in the disk with the modulus of f of z naught, which again, remember, is we're assuming is the maximum value of the modulus of f in the disk, is greater than, oh sorry, strictly greater than the modulus of f of z1. Right? That is to say, if we're non-constant, then I have to be a different value somewhere. And we're assuming this is the maximum, so this has to be larger than that value. The modulus of that value. Sorry.
Clarifying question. When you say in the disk, you mean only in the interior, not the boundary?
Yes. Right. Of course, remember, analyticity is defined in an open neighborhood, so I can't include the boundary because I can approach the derivative from different ways outside the domain of analyticity. Okay. So, just some notation. Let's let C sub r be a circle as per usual with radius capital R. Centered at Z naught. Passing through Z1, right? This uniquely determines a circle. I take the center and I insist that I pass through some point that basically just determines the radius, right? The distance between Z0 and Z1. Okay. Then, what does this tell us? The modulus of f of z naught is less than or equal to, I'm sorry, greater than or equal to the modulus of f of z for all z on this circle CR. Okay? Right, so yeah. No, the important thing to note here is that I lose the strictness. I want to somehow argue that I can restore that. Okay. So, since f, or really I should say modulus f, is continuous. I hope you believe me there. We haven't actually proved that taking the modulus is continuous. We know it's not analytic, but in fact it is continuous. Since the modulus of f is continuous, the modulus of f of z must be strictly greater than the modulus of f of z, for some segment of CR containing the point Z1. Okay. Now, let's apply the Cauchy integral formula. F of z naught is equal to 1 over 2 pi I times the integral along CR. Remember, I'll use this notation for insisting that CR be positively oriented and traversed once. Okay, of f of z divided by v minus z naught dz. Okay, now I'll kind of use a blended perspective here and try to compute this integral somewhat by brute force. What do I mean by that? I mean, I'll parameterize C sub r, plug it in to the Cauchy integral formula. We developed these tools to try to, these integration tools to try to avoid having to do this explicit type of calculation, but sometimes this is the way that we proceed to actually prove things. Okay. So this is equal to, I'm sorry, I forgot my constant. 1 over 2 pi I times the integral from 0 to 2 pi of, how do I parameterize my circle C sub r? I'll just do the standard thing that I always do for a circle, right? I'll just take my center point and add r times e to the it. Yeah. Okay. So f of z naught plus R e to the IT divided by R e to the IT, right? Because I subtracted a Z naught from the Cauchy integral formula, times the derivative of this parameterization, right? Which is just I times R e to the IT dt. Okay. So we get some cancellations here, right? We get rid of an I. We get rid of this RT. Yeah. Okay, so altogether, what is this? 1 over 2 pi times the integral from 0 to 2 pi of f of Z naught plus R e to the IT t. Okay. So take a step back here. What have we done? We've expressed the value of f at Z naught as the average, in a certain sense, of its values around the boundary along this circle, CR. Okay? So, that is to say, so f of Z naught has been expressed as the average of its values on the circle C sub R. So you might encounter this terminology in the textbook or elsewhere. This is called the mean value property. Much similar to the mean value theorem from real calculus. Okay. So let me leave you with this. Use this to finish the argument. We'll leave that as an open square because you will fill it in. Okay. So, we had a question earlier this term about what is a lemma, right? It's a standing point, a place where we gird ourselves to make a more sweeping general argument. Notice in the hypothesis of this statement, I made a very specific statement, right? I insisted that I work in a disk where the maximum value is assumed at the center of that disk. Now, let us generalize this and use this lemma to prove something much more powerful. Okay, so maximum modulus principle. Okay, so if F is analytic in domain D, and let us say that the modulus of f of z attains its maximum, at some point, Z naught contained in D, then F is constant in D. Okay. So, again, we come up against this notion of how restrictive the notion of analyticity is. It's all or nothing. Either we attain a maximum on the boundary of some domain D, or if we attain it somewhere inside, then it must be a constant. I think we probably have just enough time to outline the argument. Okay, so first of all, let's just say that it suffices to show that the modulus of F is constant in D. And that actually takes a tiny argument to make, but I'm confident that you can do that. So we'll assume by contradiction that that the modulus of F is non-constant in D. Okay, so then similar to our argument in our last proof, there is some Z1 in D, which is strictly less. I'm sorry, that has modulus of F of Z1 strictly less than the modulus of F of Z naught, the thing that we assumed, the place where we assumed F attains its maximum. Okay.
Can we say that it's just a Z1 is an L1 of D, because wouldn't that also include the boundary?
No, because D is a domain.
Right, okay, yeah.
Yeah, we'll say something more specific about the boundary. That'll be our next result, which we'll get to on Friday. But yeah, so I kind of jumped ahead by saying anything about the boundary. Right? We're still considering D as just a domain, open and connected. Okay, so right, we take Z1 in D, and let gamma be a path in D, connecting Z naught and Z1. Sorry, I shouldn't say and here, I should say 2, because I want gamma to be oriented. I start at Z1 and go, I'm sorry, I start at Z naught and go to Z1. Okay? let us consider the modulus of f of z for z lying on this smooth contour gamma. Okay. Here's a bit of a leap, which surprisingly is somewhat related to our discussion of the real numbers. The axioms of R, which is an unambiguous statement because we're assuming the law of the excluded middle. The axioms of R guarantee there exists a point W lying on gamma so that two things. The modulus of f of z is equal to the modulus of f of z naught for all z on gamma before W. They occur in the parameterization of gamma before, right? Remember, this is implicitly relying on the fact that we impose a order relation on the points that lie on gamma based on how we parameterize gamma. Okay, and secondly, there are points z on gamma arbitrarily close to W with the modulus of z, the modulus of f of z strictly less than the modulus of f of z naught, where we assume our maximum value. Okay, so we don't have time to finish this argument, but think about what this means for a second. That is to say, somewhere along gamma, we will stop assuming our maximum value, right? That's basically what this is saying. I start out, the way I constructed gamma is I start out at z naught, where the modulus of f assumes its maximum value, and at some point along that curve, gamma, I'll stop assuming the maximum value. Yeah? Okay? And, yeah, what does this second condition mean? Well, I'm out of time, I guess. Think about that before Friday. We'll pick up there. Okay? Good, so enjoy the afternoon, and I'll see you Friday. Yeah, expect some communication on campus over the next 12 hours. I'll be generous to myself.
I was looking more into the conversation before
Yeah, you did. That's okay. Yeah.
but I dressed up in the right problem, but I did it myself.
Okay.
Went up the orange problem,
Sure.
and I had to, and the transist, it was kind of cool, I ended up coming up IZ minus e to the negative IZ over 2I.
Yeah,
You end up getting that.
great.
And I just like, should I give hints and stuff in these problems?
I give hints. I think that's fine.
Yeah.
I like hints.
Yeah, hints don't
Yeah,
hurt.
When I was going through it, I had to look up the formulas for if you multiply sines and cosines, how the angle.
That's some of the most justified hints. It's like,
Yeah.
you might not remember this trigonometric identity. Use this.
Yeah, thank you.
Yep.
Good one.
So I sent you an email and I just wanted to check in. So I'm thinking about doing mine on the Newtonians.
Yeah.
I know that myself included, most people don't really know anything about them.
Yeah.
So-
Completely expository. That sounds great.
Okay, I was gonna say, and then just sort of, I guess at some point in it, after I've given the basic explanation, talk about what they were originally used for, and then how now they're used in stuff like the complex numbers, their sort of relation to it.
Yeah. That's great. And if you have the time or interest, I would say, quaternions are find quite the application in coding up rotations. So yeah, this is an interesting correspondence that you can take a rotation matrix in 3 space and generate a quaternion, and vice versa.
I can see, yeah, because I found an 18-page review on a book about quaternions and octonians.
Yeah.
And I've read the first couple of pages of it, and he was talking about how the quaternions were originally developed as a way to work with 3D geometry.
Yeah.
And then I guess Dot and Cross Project came in and kind of took away their thunder. But
Yeah, but as a matter of fact, a lot of visual processing of rotations are still implemented
it's still done with.
quaternianically.
Okay, yeah. So I am going to do more of a, I guess high level overview of the kind of stuff.
Sure. That sounds great.
And then would my paper then just be more of a similar thing? And so instead of diving into a very specific application, just give an overview and then a couple of ideas or examples?
Yeah. I would say I would like to see some type of application.
Oh, definitely.
But yeah.
Okay, cool.
That sounds great.
Thank you.
Yep.
Have a nice day.
Have a good afternoon.